So let's do a couple of quick examples. Let's say that we have a 12-volt battery and I have two capacitors here in series, C1 and C2. C1 is going to be 21.5 microfarads and C2 is 41.6 microfarads. I close the switch, current flows, charge happens, and so I want to know what is the charge and voltage on each one of these. So I want to know Q1 and I want to know Q2 and I want to know V1 and I want to know V2. Okay, so well, we know they're in series, so that means that Q1 equals Q2. So whatever that is, it's equal to one another. They're in series, so that we know that V1 plus V2 equals the original 12 volts. Okay. We also know that I could replace those two capacitors with an equivalent capacitor. So what's the equivalent capacitor? 1 over equivalent capacitor is going to be 1 over 21.5 microfarads plus 1 over 41.6 microfarads. So the equivalent capacitance is going to be equal to 14.2 microfarads. Now, if this is my configuration right here, then there's going to be a charge on there. And so we know that the charge, we know that C equals Q over V. So the charge is going to be C times V. So that would be 14.2 times 10 to the minus 6 farads times 12 volts. And so that would give me a charge of 1.70 times 10 to the minus 4 coulombs. Or if you really wanted to write it, you could write that as 0.170 millicoulombs. I don't really care. They both say the same thing, so either one is correct. You could also say, if you really don't like either one of those, you could say this is 170 microcoulombs. Okay. So all three statements are identical, and I would accept any of those three on a test. Okay, because I don't really care. It all says the same thing. So now we know that Q1 is going to be equal to 0.17 millicoulombs. We know that Q2 is 0.17 millicoulombs. So we answered those two questions right now. Now I want to know, what are the V's? Okay, so what's V1 and V2? Well, we know that V is going to be equal to Q over C. So V1 is going to be equal to the 1.7 times 10 to the minus 4 coulombs divided by the 21.5 microfarads. And so that means that V1 is going to be equal to 7.92 volts. V2 is going to be the 1.7 times 10 to the minus 4 coulombs divided by the 41.6 microfarads. Remember, micros 10 to the minus 6. So V2 comes out to be equal to 4.18 volts. Okay, now if we did this right, we can check ourselves, because we know that V1 plus V2 should equal V0. That should be 12 volts. So when I add these up, I get 12.1 volts. That is correct to within rounding error. Remember, that last digit is your least significant digit. It's a 0.1. Well, that least significant means that could equally be a 0.0 or a 0.2. So that means that this is correct within rounding. So now we have this, and notice that we connected across a 12-volt battery. Neither of those had 12 volts on them. the sum was 12 volts. But neither one of those actually had 12 volts on it. This is a mistake that students often make on a test. They'll just assume everything has the same voltage as the battery. And clearly, that is incorrect. Well, now let's do another example. So now let's do an example in which we have the same 12-volt battery and the same two capacitors, but we're now going to connect them up in this way. So this is C1, that's C2. So C1 is still going to be equal to 21.5 microfarads. C2 is still going to be 41.6 microfarads. So now I close the switch, current flows, and charge distributes here. Okay, so we have a Q1 on that capacitor and a Q2 on C2. So what we know now is that V1 equals V2, that's equal to 12 volts. Okay, because this is all one conductor there, this is all one conductor there. Conductors are equipotential, so that this is all the difference in the voltage here is the same as the difference in voltage everywhere. Okay. So now we got that, and so we say, oh, well, now it's easy because now I know that Q is CV. So Q1 is going to be equal to 21.5 times 10 to the minus 6 farads times 12 volts. So Q1 is going to be 2.58. So this is 2.58 times 10 to the minus 4 coulombs. Okay. Q2 is going to be equal to 41.6 times 10 to the minus 6 farads times 12 volts. So Q2 comes out to be 7.57 times 10 to the minus 4th coulombs. Okay. So V1, 12 volts, V2, 12 volts, Q1 equals 2.58 times 10 to the minus 4 coulombs, Q2 equals 4.99 times 10 to the minus 4 coulombs. There's 4's there. Okay, now, that's one way of solving the problem, but we also know that when I connect that together, that we have an equivalent capacitance there. So what's the equivalent capacitance going to be? That's going to be C1 plus C2. So the equivalent capacitance is going to be equal to 21.5 microfarads plus 41.6 microfarads. So that means that the equivalent capacitance is going to be equal to 63.1 microfarads. All right. Well, we know that the Q, okay, is going to be C times V, so that'll be 12 volts times 63.1 microfarads, and that comes out to be 7.57 times 10 to the minus 4th coulombs. Now, that number, that's your total Q. So what happens if we add Q1 plus Q2? Because that should add up to the total. So if I add Q1 and Q2, that comes out to be 7.57 times 10 to the minus 4 coulombs, which we expect it to be. Okay, now notice what I did. I solved the problem as I asked it to be solved, and then what did I do? I went and checked an alternate way of finding what that total is to make sure that these numbers added up correctly. Now, guess what happens if they don't add up to be the same? It means you made a mistake. You might have made a mistake in the original stuff, or you might have made the mistake in the find the equivalent, but you made a mistake somewhere, and that's like a clue. Oh, wait, something's not right. On an exam, if you're doing this, if you have time, It's also a good idea to go back and check yourself to make sure it's right. Again, most of y'all are going into some form of science or engineering, and so a good scientist or a good engineer always checks to make sure things are correct. Even in computer science, it's a good idea to check to make sure things are correct. So there's frequently, when you transmit data, there's frequently a check bit that makes sure that the other bits were read correctly. And if the check bit doesn't match with what all the other bits say, usually it's like the sum of the other bits, then that means that something's wrong and the data was not read correctly. So you always should check, and that will save you mistakes.